For the next few minutes, Chuck's going to demonstrate how our new lean burn system functions. You may recall that last November you had a first-hand look at this new ignition system. Primarily, that training session gave you an overall view. Today, Chuck plans to discuss the following component functions: what they are, how they work, and where they fit into the system to develop signals for spark advance. Now, to begin with, there's much that is similar between the familiar single pickup coil distributor and our new lean burn distributor, which has two pickup coils. One pickup coil controls the spark for engine starting, and the other takes over for engine run operation. Essentially, the start pickup coil can be identified by tracing the wiring from the larger of the two connectors. It has a relatively small reluctor air gap, so it can produce a strong signal as the reluctor turns slowly during cranking. The run pickup coil connects to the smaller of the two harness connectors. It is mounted next to the distributor cap index tang. Centrifugal weights advance spark timing with engine speed, as in our other distributors. As for vacuum advance, we now get it through this vacuum transducer, which performs the spark advance control function electronically. Let's compare the mechanical and electronic vacuum advance units. In an engine with a conventional distributor, part throttle operation develops a high intake manifold vacuum, which causes the vacuum diaphragm on a conventional distributor to advance the timing for better combustion and fuel economy. When the throttle opens wider, vacuum drops, and the diaphragm returns to its no advance position. The advance then depends on centrifugal weights. In our new ignition system, the vacuum transducer reads intake manifold vacuum level and sends this information to the spark control computer. In other words, the spark advance will be the result of the intake manifold vacuum level and the amount of time at off idle. Now, moving on with our component description, we see that the new lean burn thermoquad carburetor appears to be much the same as other TQ models. However, calibration is modified to provide an air-fuel ratio of about 18:1 for middle and high speed ranges and about 16:1 for idle and off-idle operation. Besides that, the lean burn carburetor does not have an idle enrichment system or an altitude compensator as many prior models had. Here, the throttle stop screw setting prevents throttle plate closing damage and is not used for adjusting curb idle speed. A curb idle adjusting screw grounds the carburetor switch circuit when it touches the insulated contact on the solenoid plunger. In addition, we have a totally new device called a throttle position transducer. It is linked to the throttle lever by a wire hook. Here's how it functions. A metallic transducer core slides in and out as the carburetor throttle plates are closed or opened. This mechanical movement varies an electrical signal, which is sent through wiring to the spark control computer. If we connect a voltmeter to this transducer and turn the ignition key on, we can see the voltage variation as the throttle opens and closes. If the core is pulled out quickly, as it is when the throttle opens rapidly on sudden acceleration, a maximum throttle position signal is produced by the computer. The computer also senses changes in rate of reluctor impulses as engine speed varies. This input is sent to the spark control computer along with all other signals. Another signal received by the computer comes from an engine coolant switch. It grounds out the vacuum transducer circuit in the computer, so there will be no vacuum advance until the engine warms up. The vacuum transducer and coolant switch work together as a team. We also have an ambient air temperature sensor inside the computer. It reacts to the temperature of air passing through the air cleaner. In doing so, it controls the signal developed by the throttle transducer. These two also work together. Although the carburetor switch does not produce a signal as such, it grounds out the vacuum transducer circuit when the throttle plates close. And not until the idle speed screw opens the ground circuit is the computer able to produce vacuum advance in direct proportion to intake manifold vacuum. Now, under certain engine operating conditions, the throttle position transducer and the vacuum transducer both develop their signals along with engine speed. Engine speed is an additional signal to the spark control computer, but does not result in additional advance. Now, let's take each component function separately. First, let's point out that all engine spark timing and advance references that follow are given in crankshaft degrees. And for simplicity, we will ignore the centrifugal advance input. Let's begin by cranking the engine. During the cranking period, spark timing is determined by the fixed physical position of the start pickup coil in the distributor. This fixed signal of 4 to 10 degrees is used primarily for starting. As the engine starts, the computer senses increasing engine speed, then overrides the start pickup signal electronically and transfers to the run pickup coil signal. The engine now runs at the basic spark timing setting, plus as much as 9 degrees of extra advance, depending upon engine speed. After the engine runs for about 1.5 minutes, the extra spark advance cancels out in the computer and spark timing returns to its basic setting, where it remains until we open the throttle. Now, if engine coolant temperature is below 150 degrees, the coolant switch remains closed. As a result, spark advance cannot be produced by manifold vacuum. Therefore, it is the throttle position transducer that signals the computer, and spark timing immediately advances about 5 degrees in addition to whatever centrifugal advance is present. If we open the throttle plates to wide open position, the throttle transducer signal to the computer will produce about 10 degrees advance, raising the spark timing to 20 degrees plus any centrifugal advance. This will only happen when the ambient air temperature sensor in the computer is below 75 degrees. The engine then receives that full 10 degrees. On the other hand, if carburetor intake air is about 105 degrees, the sensor will signal the computer to give only about 1/2 of that advance to the engine. As we continue driving, the coolant switch opens when engine coolant temperature climbs to 150 degrees or above. Now the computer can receive signals from the vacuum transducer. For each minute that the vacuum transducer receives 16 inches of vacuum or more and the carburetor switch remains open, the spark control computer will begin to advance spark timing of the engine from the basic setting to an advance of about 5 degrees. This additional spark advance is then electronically stored in the computer. In 7 minutes of driving without returning to idle, spark timing of the engine will advance to its maximum of 35 degrees, with 35 degrees stored in the computer memory. But at times, the throttle must be released when we slow down or stop. And the moment the curb idle speed screw touches the carburetor switch contact, the vacuum transducer circuit is grounded. Two things happen immediately. First, all 35 degrees of spark timing at the engine produced by the vacuum transducer signal is immediately canceled out. However, the computer puts those 35 degrees of spark advance into its memory. Now, for every minute the throttle carburetor switch remains closed, the spark advance stored in the computer memory begins to count down about 10 degrees. After 3.5 minutes, all memory of spark advance stored in the spark control computer from the vacuum transducer signal is wiped out. Now, let's begin once again and assume that we have 35 degrees stored in the memory side of the computer and the throttle closes for only 1/2 a minute. In that time, 5 degrees will count down, leaving 30 degrees remaining. Now, when we reopen the throttle and manifold vacuum is at 16 inches or more, the memory of the 30 degrees of spark advance remaining in the computer memory is immediately put back into effect, and the plugs now fire at 40 degrees spark advance. Just remember, whenever some amount of vacuum advance remains stored in the memory, the computer puts it back into the ignition system the instant the throttle is reopened and vacuum rises. Now, whether there's 3, 15, or 25 degrees remaining, the computer starts to count up once again to the maximum of 35 degrees advance, but can only reach this maximum when manifold vacuum holds at 16 inches or more. Actually, the timing will advance with any vacuum level above 0 as long as the carburetor switch remains open. Now let's talk about spark advance when we go to a wide open throttle. As only one example, let's assume additional advance from the vacuum transducer is 15 degrees. If at that moment we go to a wide open throttle, the sudden drop in vacuum causes any engine spark advance developed in the computer by the vacuum transducer to drop out immediately. Yet, the memory of whatever spark advance was programmed into the computer does not begin to count down unless the carburetor switch closes. When the throttle is returned to a position where manifold vacuum comes back up, whatever spark advance was programmed into the computer is now put back into the total spark timing of the engine. Now let's talk about engine speed and its effect on distributor centrifugal weight advance. As engine speed increases, the further the centrifugal weights move outward. As a result, our run pickup signal comes in faster for additional advance and can develop a maximum centrifugal advance of 11 to 18 degrees at 4,000 RPM. Now, because of this precise control of spark timing, it's a clean engine at all speed and load conditions. And remember, your reference book has expanded coverage about this new ignition system. The next training session will cover diagnosis and service of the total system. See you then.